Electricity is the lifeblood of modern society, powering our homes, businesses, and industries. To ensure the efficient and reliable delivery of electricity, a complex system of power generation, transmission, and distribution is in place. At the heart of the distribution network lies the distribution electrical transformer, a vital component that enables the safe and effective distribution of electrical power to end users. Before delving into the specifics of distribution electrical transformers, it is essential to understand the broader context of electrical power distribution. Power generation plants generate electricity at high voltages, typically ranging from thousands to hundreds of thousands of volts. This high-voltage electricity is transmitted over long distances through high-voltage transmission lines, also known as the grid. Distribution transformers are key components of the electrical grid infrastructure, serving several crucial functions. Distribution transformers step down the high-voltage electricity received from the transmission lines to lower voltages suitable for distribution. In most cases, they reduce the voltage to levels commonly used in residential and commercial applications, such as 120 by 240 volts or 230 by 400 volts, depending on the regional electrical standards. Distribution transformers distribute electrical power to various areas or feeders within a distribution network. They ensure that electricity is evenly distributed among the connected consumers, taking into account the varying power demands throughout the network. Distribution transformers provide electrical isolation between the distribution network and the end users. This isolation helps protect sensitive electrical equipment and appliances from voltage fluctuations and disturbances that may occur upstream in the transmission system. Distribution transformers contribute to improving power quality by minimizing voltage fluctuations, harmonic distortions, and other electrical anomalies. They help maintain stable voltage levels within acceptable limits, ensuring efficient operation of electrical devices and reducing the risk of damage. The development of distribution electrical transformers traces back to the late 19th century when electricity started to become more widespread. The pioneering work of inventors such as Nikola Tesla and George Westinghouse laid the foundation for the alternating current AC distribution system that we rely on today. The early distribution transformers were relatively simple, consisting of iron cores and primary and secondary windings. Over the years, advancements in materials, insulation systems, and manufacturing processes have led to the development of more efficient and compact distribution transformers. Today, distribution transformers come in various sizes, designs, and configurations, tailored to meet specific application requirements and regional electrical standards. To comprehend how transformers operate, it is necessary to grasp the basics of electromagnetism. Electromagnetism is the branch of physics that deals with the interaction of electric currents or fields and magnetic fields. Key concepts include electric charge, electric current, magnetic fields, and electromagnetic induction. A distribution transformer consists of two essential components, a primary winding and a secondary winding, both wound around a magnetic core. The core is typically made of high permeability materials such as laminated silicon steel, which facilitate magnetic flux flow. When an alternating current AC flows through the primary winding, it generates an alternating magnetic field in the core. This alternating magnetic field induces a corresponding alternating voltage in the secondary winding, thanks to the principle of electromagnetic induction. The voltage induced in the secondary winding is directly proportional to the turns ratio between the primary and secondary windings. Transformers come in various types and configurations to meet specific voltage requirements and applications. The most common types include single-phase transformers. Single-phase transformers are used for residential and small commercial applications. They have a primary and secondary winding, providing a step-down or step-up voltage transformation. Three-phase transformers are employed in industrial and commercial settings, where three-phase electrical power is prevalent. They consist of three sets of windings, each connected to a different phase, enabling efficient three-phase voltage transformation. Autotransformers are a special type of transformer where a portion of the winding serves as both the primary and secondary winding. Autotransformers are used for voltage adjustments, as they provide a variable or tapped output voltage. Transformers are not perfectly efficient, and energy losses occur during operation. These losses include copper losses in the windings due to electrical resistance and core losses due to hysteresis and eddy currents. Transformers are designed to minimize these losses and improve overall efficiency. Transformer efficiency is defined as the ratio of output power secondary power to input power primary power. Factors such as load conditions, transformer design, and core materials influence efficiency. Transformers typically operate most efficiently at or near their rated load capacity. The core of a distribution transformer serves as a path for magnetic flux and plays a crucial role in its operation. The core is typically made of laminated silicon steel, which provides high magnetic permeability and low core losses. The laminations are insulated from each other to minimize eddy current losses. The core's design is optimized to minimize magnetic flux leakage and maximize magnetic coupling between the primary and secondary windings. Different core configurations, such as shell type or core type, are employed based on specific requirements and application considerations. The windings of a distribution transformer are responsible for transferring electrical energy between the primary and secondary circuits. They are typically made of copper or aluminum conductors and can be either cylindrical or disc-type in shape. The windings are insulated to ensure electrical isolation and protect against short circuits. Insulation materials such as paper, cellulose, and synthetic resins are used to separate the conductors and prevent electrical breakdown. Insulation systems undergo rigorous testing to ensure they can withstand the expected electrical and thermal stresses. Distribution transformers are housed in a tank that provides mechanical protection and insulation. The tank is typically made of steel and designed to withstand the operating pressures and environmental conditions. Cooling methods are employed to dissipate heat generated during transformer operation. Common cooling methods include natural convection air-cooled, forced air, and liquid cooling. Oil-cooled transformers use mineral oil as a coolant, while some transformers employ alternative fluids. Distribution transformers are connected in various configurations based on specific system requirements. Common connection types include delta-delta, delta-Y, Y-delta, and Y-Y. These configurations determine the primary and secondary winding connections and affect the voltage transformation characteristics. Tap changers allow for voltage adjustments to accommodate variations in the supply voltage or load conditions. On-load tap changers OLTC enable voltage regulation while the transformer is energized, while off-circuit tap changers OCTC require the transformer to be de-energized for tap changes. The power rating of a distribution transformer determines its capacity to handle electrical load. The power rating is typically expressed in volt-amperes VA or kilovolt-amperes kVA. It represents the maximum power that the transformer can deliver without exceeding its thermal limits. To determine the power rating required for a specific application, factors such as the connected load, expected load growth, diversity factor, and power factor must be considered. Accurate load assessments and future projections are crucial to avoid undersizing or oversizing the transformer, which can impact efficiency and reliability. Distribution transformers are designed to provide specific voltage transformation ratios. The turns ratio, which represents the ratio of primary to secondary winding turns, determines the voltage transformation. For example, a transformer with a turns ratio of 2:1 will step down the primary voltage by a factor of 2. In addition to the turns ratio, transformers may include tapping arrangements that allow for minor adjustments to the output voltage. These taps are typically located on the primary winding and provide flexibility to accommodate variations in the supply voltage or load requirements. Voltage regulation is an important aspect of transformer operation, ensuring that the output voltage remains within acceptable limits under varying load conditions. Transformers are designed to provide voltage regulation within specific tolerances to meet regulatory standards and ensure consistent power quality. Voltage control methods may include on-load tap changers OLTC or off-circuit tap changers OCTC, which allow for adjustments in the turns ratio and hence the output voltage. These tap changers enable fine-tuning of the output voltage to compensate